Hi, Scott. It's Tommy again.
Hey, Tommy.
All right, good. Just making sure you're in.
Yep.
we'll wait a few more minutes as people are joining in. So it's 12 now, our time. So give about 2 or 3 more minutes, and then I'll turn it over to Jim Rickles for the announcement. Okay, we could begin. Again, I'd like to welcome everyone to the continuing NERI LEHIGH seminar series today. And at this time, I'd like to ask Dr. Jim Rickles to please introduce our presenter and speaker for today.
Yeah, thanks, Tommy. Can everyone hear me okay? You hear me okay, Tommy?
All good, yep.
Oh, okay, yeah, I'm Jim Rickles, the director of the NERI facility at Lehigh University and a faculty member of the Civil Engineering Department. I'd like to introduce our speaker today, Dr. Scott Harvey. He's a professor in the School of Engineering, Environmental Science at the University of Oklahoma. And he has several research interests, one of them being his primary focus is on enhancing the behavior of the built environment and increasing building and bridge resilience through the development of response modification devices, one of which he'll present today. And Scott has led several research projects, including those funded by NSF, the DOT in Oklahoma, and also one funded by ABC-UTC. And Scott has his degrees from Duke University as a registered engineer in the state of Oklahoma. What I'd like to do is to then introduce the speaker further by noting that the title for today's presentation is Advancements in Light-Payload, Seismic Isolation, Theory Experiments and Future Needs. And at the end of the presentation, we'll have some time there for speakers to, for the speaker to entertain questions. I think, Tommy, in the meantime, they could send in blogs to you, right, that you could then read the question if you wish. I think there's a way to do that as well.
Yes, I was going to note that there is a group chat that if you have questions during the presentation, you may type them there, or you can wait toward the end, at the end of the presentation to ask questions.
Okay, and we actually have a snowstorm there, and the university closes at 1 o'clock, so we'll be very brief somewhat towards the end. But without further ado, let me go ahead and hand the podium over to Scott. So welcome, Scott, and we'll let you proceed there.
Thanks, Scott. This time you could share your screen. Great, we can see it.
Okay, so thanks for the introduction, Jim. Thanks for this opportunity to LEHIGH NERI site for hosting this and inviting me to give a talk. Today I just want to share some of the work that we've been doing here at the University of Oklahoma on light payload seismic isolation. Just going to give some overview of advancements we've been making in the theory and experiments on these systems, as well as some of the future needs that we've identified through the work. So first, to give a little bit of background and motivation for the problem, community resilience is a topic that's on everybody's minds right now. So this should be a familiar image, this loss triangle or the resilience triangle. So a community or a building or a piece of equipment has some nominal operating conditions, some nominal functioning capacity at which it's going to be operating at. And then when it's struck by a disaster, it's going to lose some level of functionality. Depending on the robustness, the loss of functionality is going to vary. And then also depending on measures taken, the rapidity at which it'll approach its nominal functionality will change. So we have various techniques that we can use to try to enhance the resilience, either by increasing the robustness prior to the event or taking some measures that'll increase that rapidity following the disaster. Broadly, earthquake risk is associated with casualties, loss of life, injuries, fatalities. This is paramount as civil engineers that we maintain a healthy population to the person, but then also we need to talk about economic losses as well. Those are in the form of direct economic losses, so the need for repair and replacement costs following an event. Maybe there is some equipment that gets damaged that needs to be replaced, or even a building collapsing. This is going to incur some economic losses. As well as those direct losses, there's also indirect losses. So for example, business interruption. If a system goes offline and it's not able to provide a service, then it's going to disrupt business, which may cost money per hour or minute of downtime. Also, there's displacement of residents and services if a building should be condemned. These risks are all incorporated into seismic performance criteria to which we design to. So depending on the ground motion intensity or design level being considered, the building and its contents need to be performing at a specified level. Here, most of the work that I've been looking at is on essential facilities. So these are buildings and structures that are intended for use during the post-earthquake recovery. This includes police and fire stations, hospitals, and emergency response centers. So we can look, depending on, again, the earthquake intensity, what level of functionality we should achieve. Collapse prevention is the highest performance level, and then next comes life safety. And then here, talking about operational. So under low-level events, we need to be able to maintain fully operational conditions. This is going to aid in the recovery process and ensure that we don't incur some of those losses I previously mentioned. Even under more rare events, these essential facilities need to maintain operation. Otherwise, again, it's going to hurt the recovery process. So here, a lot of times business disruption is associated with damage or disruption of equipment housed within the essential facilities. So a lot of these facilities have what we're going to call mission critical equipment. For example, some sort of telecommunication device that needs to maintain operation, medical equipment, or just objects that may disrupt egress into a building. However, a lot of this equipment tends to be sensitive to strong floor motion. So for example, a hard drive is typically rated about 30% of a G, and if it should exceed those levels, it's going to go offline and disrupt operations. Also, with medical equipment that's on wheels or casters, they can slide or roll around, again, blocking egress points and just overall causing disruption. And then finally, a lot of this equipment tends to be quite slender, so you can experience rocking or overturning to cabinets, which is going to be the focus here, but also you can talk about art in this sense too. So there's going to be some direct losses if you're damaging artwork. So the problem that we face then is that this vibration sensitive equipment is susceptible to harsh floor motion. So if we bolt it down to the floor, then those floor vibrations are going to be transmitted directly into the equipment, or in this case, this cabinet. That's going to induce large accelerations and potential failures. So the solution that we've been looking at is base isolation. Here, actually isolating individual contents of the building or multiple pieces of equipment, as we'll talk about later. And so the basic premise, like seismic isolation for buildings, is to detune the equipment from the disturbance using some sort of device. Here, the device that we'll be looking at is rolling type isolation systems. However, for this sort of payload, there's many devices out there. In doing this, we're going to reduce the acceleration sustained by this sensitive equipment and hopefully maintain its operation during and following the earthquake. So we're going to eliminate that business interruption following the event and aid in the recovery process. So again, the type of isolation that I'm primarily interested in is what's called rolling type seismic isolation. So to give you an overview of what I'm talking about here, there's some top frame or platform on which the equipment would rest. Then you have a bottom frame that's going to be resting on the floor, receiving the excitation. And then located within these frames are bearings. So here a rolling bearing is comprised of a steel ball interposed between a concave up ball and a concave down ball on the top surface. Being that they're concave, when you experience a lateral translation, that in turn induces a vertical motion, so a change of potential energy that'll give you this gravitational recentering force. So a lot of times you'll hear these called rolling pendulum isolation systems. The fact that the mass ends up not coming into play in terms of the frequency because the gravitational restoring forces are mass proportional as well. These systems are quite simple to fabricate. Again, you just have the two dishes and a steel ball. They're easily extendable to multiple cabinets. So here at a typical facility, you're not necessarily going to have one piece of equipment standing on the floor that needs to be isolated. You may have multiple cabinets or racks that need to be isolated. So they're easily extendable to, in this case, up to about 8 or 10. So just sort of by chaining them out in such a fashion. So in the broad field of seismic isolation, we're really looking right here at what we're calling light payload isolation. So that's masses that are being isolated are on the order of 10 kilonewtons. So single racks or server cabinets, potentially even isolating an entire floor within a building. So this would be one bay within a building where you can isolate this raised floor. So using bearings placed around. And here now you're protecting an even larger mass, which I'll discuss a little bit further later. And then if we move up the spectrum of seismic isolation, we get into moderate payloads. So some of the recent work looking at residential homes being isolated. So talking now about 100 kilonewtons, all the way up into heavy payloads, where we're doing multi-story buildings or bridges. So again, the focus is on rolling isolation here, which is a very affordable and easy to implement means for light payloads. The application of these sorts of systems to heavier payloads is questionable due to the steel ball. You have a stress concentration that under large loads can cause durability issues. Okay, so to kick it off, I would just want to give some results that we recently conducted from some experimental tests. These were actually conducted at the University of Alabama, where we're trying to see how well these systems performed under operating conditions. So here, we're actually looking at real network cabinets. So they're about 2 feet wide, 4 feet deep, and 6 feet tall. Their total mass for a single cabinet is 7 kilonewtons. So again, on the lighter side. And then these were loaded down such that the mass was representative of one of these in service. So you have a center of mass that was located above the wheels, but then also front of center, producing an eccentricity that will come into play in terms of the response. These cabinets were isolated with a rolling isolation platform, which you can see here. So these are quite low profile. You're looking at 3 to 4 inches in depth. And the particular rolling pendulum bearings that we're using have a nominal displacement capacity of about 18 centimeters. So if the ball were to displace 1 full radius in the bottom dish, 1 full radius in the top dish, then you'd be able to displace up to 18 centimeters before you hit a rigid lip that's going to constitute an impact, which is critical for these systems. Over the remaining portion, so inside that lip, these are designed to be conical in shape, so they have a 1 to 10 slope. Being that this is a pendulum type mechanism, the restoring force is related to the weight mg times the slope of the dish. So by constraining the slope to be 1 to 10, we're effectively constraining the sustained accelerations to be 1/10 of a g. So this is a very common designed for this sort of system. If instead it was spherical, then you would be talking about a linear restoring force, but here, being that it's conical, it's actually highly nonlinear. And then also another variation that we were looking at was how the treatment of the dishes or the rolling surfaces affect their performance. So looking at a bare stainless steel dish versus an elastomeric damping line dish. So here's the setup that we're using at the University of Alabama. So this is a uniaxial shake table. So the excitation is going to be in this direction. We had an array of sensors to measure both the table's motion, the isolation platform's motion, as well as the cabinet's motion. So we had an LVDT and a uniaxial accelerometer attached to the table to capture the ground's motion. At the base of the cabinet, just above the isolation layer, we had 3 string potentiometers and 2 triaxial accelerometers. The potentiometers were arranged such that we could get the longitudinal motion across the bearing, as well as the transverse displacement and rotations. The accelerometers were likewise located so that we could capture the full motion across the isolation system. We were also interested in what was happening within the cabinet. So here we had an accelerometer located at the mid-height of the cabinet, as well as 2 at the top, and then a similar arrangement of potentiometers to capture the drift across the cabinet. Here I'm going to be focusing primarily on what's happening just above the isolation layer, because we're really interested in understanding the dynamics of the platform itself, not so much the cabinet's dynamics. Okay. The parametric variation was provided by the number of cabinets. So here we looked at configurations where we had a single cabinet being isolated as well as a ganged configuration. So again, in a data center or some sort of facility, they're probably not going to have just a single cabinet that needs to be isolated. Typically, you're going to see multiple units. Here we only tested up till 2 cabinets, but then you could expect that, right, sometimes you may see again up to 8 or even 10 of these ganged together. The orientation, we looked at side to side, so shaking through the side of this cabinet as well as front to back, shown on the right. In the side to side orientation, again, because there is a mass eccentricity, we expect to see larger rotations. Also, this cabinet is quite slender in the side to side orientation, which we'll see come through in the data. And then here, just to visualize what I was talking about with the rolling surfaces, there's the bare stainless steel dishes, as well as the same dish just lined with an elastomeric layer. The disturbance that we were looking at was the Vertex 2 Zone 4 ground motion. So this is put out, this is a standard for network equipment qualification testing. So here is the acceleration record. This is a DBE level event, so 10% probability of exceedance in 50 years. It's a pretty strong motion, so a PGA of about 1.6 G. And then here's the corresponding spectrum. So with a lot of frequency content between 1 and 10 hertz. This record was actually synthesized so that it would be representative of a lot of potential installations for a cabinet. So potentially within the building in various locations, so up to the roof all the way down to the ground, as well as varying structures themselves, so different frequency contents. So now just for some of the experimental results from these tests. So I'll start off by showing a video. So this is a camera looking longitudinally at the table. So this is in the side-to-side orientation for a bare steel dish. So you'll see the table's going to move away from us. Okay, so a few things to note. Because of the eccentricity, we're seeing quite a bit of rotation within the cabinet. And even though we're applying a uniaxial motion, we're still getting rotations. Also, you can see a little bit of rocking within the cabinet out of plane here. And then finally, there could have been some audible clicking sound. That was actually the ball impacting with the edges or the lips of the dish. And if we look at what those results are from the sensors, we have the longitudinal displacement across the isolation layer, the longitudinal acceleration, the total acceleration just above the isolation layer, as well as the rotations across the isolation layer. So here, longitudinal displacements are on the order of about 17 centimeters, and so recall that these systems had a capacity of 18, so we're just about reaching their capacities. In terms of the longitudinal acceleration, you can see a higher frequency content going on there, which is related to the rocking motion within the cabinet. This is superimposed on what's effectively a square wave due to the bowl shape. And then finally, note here that we had quite large rotations up to about 8 degrees, resulting from that eccentricity. In addition to the side-to-side test, we also conducted tests in the front-to-back direction. In this case, the rotations were a little bit smaller. However, even though we don't have that mass eccentricity, imperfections in the system still produce rotations. So we really can't get away with using uniaxial models in this case. However, those rotations are smaller, so a lot more of the energy is being diverted into the longitudinal motion. So we're seeing displacements in excess of the capacity. And as a result, you can see distinct spikes in the acceleration where you have impacts. Note also here, we're not seeing the high frequency content in the accelerations. This is because, again, in the front to back direction, the cabinet's a lot less slender, so we're not getting that rocking effect. And again, we ran some tests at the single cabinet, and then also if we go to the gain cabinet, the results look very similar. Again, displacements on the order of the capacity with distinct impacts in both cases. The rotations are a little bit smaller in this case, and a few things to note is in the front to back orientation, initially you have very small rotations. However, there's a slight impact at this point, which then induces rotation. So we're having a clear coupling between the longitudinal response and the rotational response, especially in the case of impacts. Okay, so just a few of the observations that I've highlighted there. Significant rotations developed, and in some cases this led to premature impacts. So just because our displacements weren't necessarily exceeding the 18 centimeters at the centroid of the cabinet, because of the rotations at the extremities, we're actually exceeding the bearings capacities. So this says the rotational coupling cannot be ignored. Another observation is that at this DBE level event, the displacement demands exceeded the capacity for the bare steel rolling bearings. This motivates the need to either increase the capacity of these systems, so moving up from that 18 centimeters, or increasing the damping. And so the latter approach there, increasing the damping, is what we want to talk about now. So here, same setup, but instead of using the bare steel dishes, actually looking at the elastomeric line dishes. So again, you can see some rocking motion in the slender direction. However, the rotations are considerably smaller. And what we can see from the time histories is that the displacements are smaller as well. So here only now 16 centimeters and 18 centimeters in the side-to-side and front-to-back directions. Again, we can see the higher frequency content from the rocking. However, the rotations are substantially smaller, and we're not seeing the impacts that we were for the other case. So this tells us that supplemental damping using these rubber-coated rolling surfaces is capable of improving the performance as we'd expect. If we increase the damping, we're going to decrease our displacements and in turn improve performance. So now I want to shift gears a little bit and actually go to some of the mathematical modeling that we've been doing of these systems. So we've seen some observations in the lab, but now we want to be able to try to capture that with predictive models, physics-based predictive models. So just a little bit on notation here. So what I'm presenting here today is an extension of previous models that we've developed in our research group. So here, considering the potential for multiple cabinets, this is a plan view, so you can see the top frame. The cabinets would be resting sort of in each of these wells, where the center planks are going to be carrying twice the load versus the outer planks. The model that we're looking at, we're considering only translational in plane motion, so translations at the base in the y and the x directions, and as a result, this is going to in turn give us some translation of the top frame relative to the bottom frame, as well as including that rotation, which we saw to be critical in the experiments. The formulation that we followed was using an energy-based approach, Lagrange's equation, so we needed to formulate the kinetic energy and the potential energy. Here, the kinetic energy, including the rotational terms. For potential energy, because this is a gravitational system, the potential energy is mainly coming from the change in gravitational potential energy. So mg, the weight of the object, times here, this is the interpolated height at the center of mass of the cabinet. A critical piece of information that we've been including in these models is the fact that the balls don't necessarily stay on the center lines. So they actually have their own dynamics that need to be modeled. And some of the tests, at the end of the test, we'd actually see that the balls were off-centered or even nearly out of the bowl. So this led us to model them using a rolling without slipping condition. So there's a prescription of what the ball's velocity is as dictated by what the upper bowl is doing relative to the lower bowl. This is a classic form of a non-holonomic constraint. So these are constraints on the velocities of our generalized coordinates versus just the generalized coordinates themselves. And so that means that we need to be careful when we go to actually apply Lagrange's equation and use the appropriate form. And so that is the non-holonomic form of Lagrange's equation. The left side here looks very familiar. The right side also looks familiar. However, you need to be careful here when applying the constraints. You have a multiplier that's going to enforce those rolling without slipping conditions, but then here you need to impose the constraint by looking at the gradient relative to the generalized velocities. And if we go through the motions of applying this equation, we get to something that looks quite familiar. So here are the equations of motion for the platform. You have your mass times acceleration terms, some dissipative terms, where the dissipative forces are going to come from the rolling resistance. Then you also have your gravitational restoring forces that are related to here, the weight of the object, the allocation, so this B is just allocating masses to each of the bearings, and then here this is the gradient of the bowl at the ball location. So you have contributions coming from the lower bowl as well as the upper bowl, and then finally on the right-hand side is the disturbance. So at the end of the day, we end up with equations that look very familiar to us. However, these need to be simulated simultaneously with the ball dynamics. So you end up having 3 equations to express the translations of the platform as well as its rotation, and then 2 more coordinates for the x and y motion of each of the balls. So now to validate this model, looking at the experimental results, now overlaying with the numerical results here for the bare steel dishes, because it's very lightly damped, we're able to get away with using a viscous damping term. And we see excellent correspondence but in all 3 of these. So displacements are nearly perfect, accelerations line up well. We're not capturing that high frequency rocking motion because the model is assuming a rigid mass. Rotationally, we develop rotations not quite to the same order as we saw experimentally. However, we see an impact here at 0.8. So I've terminated the simulation at about 8 seconds, and that's due to an impact. So you can see a large spike in the acceleration. One of the critical needs is actually to better model these impacts. So here we're using just a simple sort of Hooke's type impact model, which isn't very representative of how these impacts actually happen. So following the impact, the response is suspect, so we've actually just terminated the simulation at that point. Similarly, we get good results for the front to back direction. Here the model, because there's no mass eccentricity, doesn't develop any rotations, and we perfectly predict the very first occurrence of impacts, and we're actually able to go a little bit further before the model becomes spurious. And likewise, similar results for the ganged cabinet, so excellent agreement with the experimental observations. So the final observation coming from this is that the mathematical model demonstrates acceptable agreement with the measured response prior to impact. Therefore, we feel comfortable in using this model to predict the occurrence of impact. However, subsequent to the impact, sort of all bets are off. So what I didn't show you is the response with the elastomeric line cases. And that's because we don't currently have a validated model for the rolling resistance. When we coat the dishes, the rolling resistance goes up substantially. No longer are we talking about a lightly damped system. And so that viscous damping model is no longer valid. So a question that remains open is how to actually go about modeling these. And this is a nice lead into some of the ongoing work that we're doing in our group, as well as some of the future work we have planned. So the three items that I want to highlight today are looking at other high-performance rolling isolation solutions, also looking at isolation performance under rare events, so MCE level events, and then finally looking at some of the primary secondary system interactions, that is interactions between the isolation system and the structure that's housing this equipment. So to begin with, talking about high performance rolling isolation, two primary techniques that we've already identified that we've been working on is supplemental damping and increasing capacity. So the objective here is to analyze, assess, and optimize different high performance technologies. With the supplemental damping, we have the benefits of decreased bearing displacement. However, this is at the expense of increased accelerations. The modeling of the rolling resistance becomes quite complicated due to the load and rate dependence of that rolling resistance. So previously we've done some tests where we tried to characterize what those relationships are and then came up with phenomenological models for those. And this is what we're doing now, trying to actually tailor these for different hardnesses of the liners, as well as different thicknesses, potentially even varying thicknesses. So again, supplemental damping is going to help us with our displacement across the bearings. Another approach could be to try to increase the capacity of these systems. So the natural inclination would be just to increase the size of all the components, go with twice as big of bowls, twice as big of balls. However, this is cost prohibitive. These different components are actually increasing disproportionately with size. So we'd like to maintain sort of this compact nature of all the components while still trying to increase the capacity of the system. So previously proposed this idea of doubling the system, so stacking two systems on top of one another, where now you have a middle frame that's acting to transition the load from the base up into the equipment. In doing this, we have effectively twice the displacement capacity with using the same components as originally. However, in some preliminary tests, we were realizing that the full capacity wasn't being achieved. We weren't getting perfect displacements across both of them simultaneously. Instead, we ended up having impacts in one of the sublayers prior to full capacity being reached. Another concern was the large vertical acceleration. So we've done quite a bit of work because these are functioning on potential energy mechanism. There's going to be a vertical motion associated with horizontal motion. In the center region there, you start to have really high velocities. Those high velocities are occurring at points where you have pretty sharp curvature, so you get these centripetal accelerations that cause a jolting action as you pass through the center. When we doubled the system, these effects doubled, and so we ended up with extremely large vertical accelerations. So now what we're trying to do is actually trying to optimize these systems, these multi-unit systems, actually trying to harness the fact that we have a second high-frequency vibrational mode. By incorporating this additional layer, we've effectively doubled the degrees of freedom. So actually trying to treat these in a robust manner using an approach similar to what you'd see using TMDs. So actually trying to sap energy through the vibrations in that middle layer. Another area of interest that we're working on is isolation under rare events. So again, these essential facilities need to maintain operation at rare or even very rare level events. So how can we optimize geometries of these systems as well as impact mechanisms such that we can ensure a safe level of operation following the earthquake? So here I have a video from another test. So all the previous videos were for design basis earthquake, but now we're looking at 150% DBE, or an MCE level event. So there clearly things have gone wrong. We're starting to see impacts clearly. So we're having impacts at design basis earthquakes. So we're definitely going to have impacts at an MCE level event. You actually saw the bowls rolling out of these systems. So it's quite a hard impact. And at this point, we're just simply sliding on the top frame. So the question becomes, can we ease these impacts in some way such that they're not quite as harsh? So now what we're looking at is actually trying to benchmark the performance under an MCE level event. So trying to determine the best possible performance using optimal control. Here the idea is that we're going to optimize an impact force trajectory that's acting at the periphery of these dishes, as well as bearing parameters P over a finite horizon. So here's this integral cost functional, subject to the dynamics of the system as well as passivity constraints. So we're going to have some sort of inelastic impact that we want to model. And so here we're trying to capture what's the best possible impact we can have. Note that this is an open loop solution, so it's not really implementable in real time. However, this can motivate or guide some of the decisions that we make when we go and try to actually design a mechanism. So instead of assuming a feedback solution, right, restricting ourselves to a particular form, for example, a cubic stiffness, some sort of restraining straps, maybe a Hertz type impact model, we've now left it open to all possible solutions that fall within the passivity constraint. In doing this, we're going to be able to benchmark those other solutions that we may pursue so we can compare how close to optimal we actually are. And again, we can also look at the trajectories in terms of forces versus displacements, or forces versus velocities. They can then motivate or guide the decision as to what impact mechanism to use. Okay, and the final research area that we're moving into is actually to try to incorporate primary, secondary system interactions. So actually moving up a little bit in scale here. So instead of isolating a single piece of equipment, isolating an entire floor within a building. So here, this is a single bay within a building that's being isolated on a raised flooring system. In doing this, now we're talking about larger payloads and higher mass ratios. So that's higher isolated masses relative to the structure mass. It's typical when we go to design or analyze these sorts of systems that we assume everything is operating in sort of a one-way fashion. That is, the ground motion comes into the building, causes a floor motion. We take that floor motion, feed it into either an experimental model or a numerical model for these systems, and then find their responses. This is valid if you're sufficiently detuned, which we typically are for isolation systems, and your mass ratio is quite small. So if we're operating in this range, then the coupling between the primary and the secondary systems is okay. However, what we've seen is these systems have limited displacement capacities, and we tend to have impacts. So we're going to break those linearity assumptions that go into developing these contours. In the event of an impact, we're going to have a spreading of energy over a broad frequency spectrum. So we're going to potentially have some nonlinear interactions between the floor isolation system and the primary structure itself. So this raises two questions. The first one, will these impacts induce coupling? Do we need to model this coupling? Second, should there be coupling, can these impacts be harnessed to protect the primary structure under strong disturbances? So we've already said that under, for example, an MCE level event, it's very likely that we're going to have an impact. Can we actually tailor those impacts so that we're able to enhance the performance of the primary structural system? And so this is where we've introduced this concept of an impact-based dual mode vibration isolator absorber. Okay, so this picture shows sort of the concept. So at low seismic excitations, we want to primarily isolate the equipment. So we want to ensure uninterrupted operation of whatever the service is being provided by the isolated components. So here the primary objective is to reduce the acceleration sustained by the equipment. However, we're going to shift focus when we go to higher level events. So when you go to MCE or very rare events, then of utmost concern is actually life safety and collapse prevention. So maybe we can actually harness those impacts to try to reduce the floor level motion. So actually trying to reduce the drift within the building. I want to show some very preliminary results that we've done in the lab here at OU. So this is Fear Structural Engineering Lab, where we have a shake table, and we just want to try to demonstrate this concept. So here, this is a 3-story structure located on the 2nd floor as a piece of equipment that needs to be protected. And we've considered 3 scenarios. One where it's rigidly locked or fixed to the floor, and then 2 cases where it's isolated, one without impact and one with impact. Okay, so the test program here, we're doing a monotone function, so just a single frequency, amplitude swings up and down. So the ground acceleration, we're gradually stepping up, and then we're going to sweep back down. And as a result, we're going to get some acceleration of the isolator. In this case, it's actually just the fixed mass, as well as measuring the drift. So you can see high contrast dots, we're actually doing vision-based motion detection to measure what the response is of the structure. So for the lock system, we see this is very much a linear system. Everything is increasing linearly with the ground motion intensity. Next, we considered a case where we isolate without impact. So now we've decoupled, using a linear bearing, that mass from the floor. So if I flip forward a little bit, so now here you can see that the structure is oscillating, and due to the isolation, that mass is no longer moving. And this is apparent from the isolator acceleration. So we've very much decreased the acceleration sustained by that equipment, so we're protecting it so it can maintain operation. As a result of decoupling, please ignore me in the background of this video. As a result of the decoupling, the roof drifts actually are increasing higher than in the locked case, but still we see a nice linear response as the amplitude increases. Okay, finally we considered that same setup. However, now there's actually some limitations on what the displacement can be within the isolation system. I'm going to click forward here. We're isolating nicely. So the structure's amplitude, its drifts are gradually increasing, and then we start to see an impact. So you can see now that there's periods at which this is impacting. In terms of the response, the drift of the roof was gradually increasing, and then at this point of impact, we saw a large increase in the acceleration sustained by the isolated equipment, but there's actually a dropping of the drift in the structure. So this is switching our objective from isolation to primary structure response reduction with disturbance amplitude. Note also that due to the nonlinear nature of the system, when we swept up an amplitude and when we swept down, there were points of initiation of impact as well as cessation of impact. Those occurred at different amplitudes due to hysteresis in this nonlinear system. Okay, so to wrap it up, I hope today's talk gave you some insight into seismic isolation, in particular light payload equipment isolation, as an attractive solution to protect sensitive equipment. In doing this, you could potentially reduce the downtime and business disruption caused by earthquakes, and then overall enhancing a community's resilience, better being able to respond to earthquakes and not incurring direct and indirect losses. So some of the results that we showed, we extended physics-based models of these systems for an arbitrary number of isolated cabinets that includes rotational coupling, and we're able to successfully predict the occurrence of impacts with these models. Some of the future needs that I've noted are high-performance solutions that may be capable of withstanding an MCE level event. So we need better models of what those impacts need to look like, and also what the subsequent response is going to be if we want to predict under extreme events. Finally, trying to shift focus to a more holistic approach where we consider the building system instead of just the building and the equipment as two separate pieces. So now we need to actually consider them together and see if there can be some synergy between the two. So with that, I'd like to acknowledge NSF for support of the work on the dual mode vibration absorber. Also, I'd like to thank WorkSafe Technologies. They are the manufacturers of the isolation systems that we did the tests on at the University of Alabama. I should note that those tests were in collaboration with Dr. Wei Song. And finally, I'd like to again thank Jim and those at NERI at LEHIGH for this opportunity to present. And with that, I'd like to thank you for your attention and open up for any questions.
Yeah, thanks, Scott. Are there any questions from the audience? And also, Tommy, did anyone send in any questions that Scott could try to address?
We don't have any questions in the group chat at this time, but feel free to unmute yourself if you'd like to ask a question to start any discussion. Thank you.
Any questions from the audience? Scott, I had a question. And
Yeah,
a very interesting talk, by the way. So I had a question regarding the isolation system and displacement. I guess the impact appears to be a criteria that you have to address. Have you tried to look at, and of course this may be influenced by the type of ground motion, near fault versus far field. Have you looked at any semi-active control, any other aspects, and maybe see if that could be enhanced? Because damping helps, but it's maybe limited because, as you say, you're increasing your acceleration.
Okay, yeah, so let me maybe go back. So previously we actually looked using that optimal control technique that I mentioned, actually trying to see if semi-active control would enhance the performance. Here we're very much trying to go with the passive solution.
Mm-hmm.
Some of the challenges potentially with implementing a semi-active technique would be the fact that these are very low profile. So to get something in there that's going to be able to actuate the system may be difficult. And of course, you know, if you go to semi-active or definitely active, you can increase the performance. However, we've really primarily focused on passive solutions.
Oh, okay. And in those studies you did, I don't recall if you identified the record. Was that a natural ground motion? Or did you... No,
it's just this one here.
Oh, I'm sorry. That's probably a spectrum generated synthetic ground motion.
Yeah. So this is a spectrum compatible ground motion. So Belcore came up with this to be the desired response spectrum for floor motions. And then this is a synthetic accelerogram generated from that. Something you'll note too here is due to limitations in tables, they've actually filtered away a lot of the lower frequency content of the ground motion. So while the standard says that you need to be along this dotted line, the requirement actually only states that you need to exceed that at greater than 1 hertz.
Oh, okay. See, the thing I'm curious about in these requirements is you know, the types of you know, the frequency content basically, because you get record-to-record variability, you know, for natural records, and in particular, I was thinking again a near fault versus far field. You know, near fault conditions, as you may know, traditional base isolation sometimes has displacement concerns, and so I'm wondering in these qualification tests whether that's something that perhaps should be considered. You know, if it's not in the spec. And then the other thing is there's also another criteria, I guess, is IEEE 693. I'm wondering if you've ever, what your thoughts may be about that, or if you ever considered that. I'm not that familiar with the Belcore.
Yeah, so I know that there are other specs out there. So Belcore again is for these cabinets, and really it's not so much intended for isolation applications. And so I think that's one part of the reason that you're going to see that the frequency content's higher. This is really primarily for bolted down cabinets. So the cabinet frequency is going to be higher, obviously, than the isolation. And you raise a really good point about record-to-record variability, and this is something that we're currently looking into. So generating an ensemble of acceleration records that meet this criteria, and then how does that in turn affect the performance? This is very much a nonlinear system, so depending on what frequency content exactly you have in the record, that's going to then change what the response is. We're also looking at trying to actually generate acceleration records that capture this lower frequency. So sort of like what you're talking about with maybe a pulse sort of component, because those are known to be very bad for isolation systems due to the frequency of the isolation system itself.
Oh, okay. Thanks, Scott. Are there any questions from anyone else? I don't want to dominate the discussion, although I have another question I wanted to ask Scott.
There's a question in the group chat that is asked, have you considered any studies on the rubber steel plate bearings?
Yeah, so with this light of a payload, maybe if I jump out. Oh, sorry. So if we go maybe to this, with the light payloads that we're talking about, lead rubber doesn't really scale that well down to that small of scales. So you need very light damping, and it's very hard to get a soft enough bearing. So we really like using these pendulum systems because they're mass independent. They function under a pendulum mechanism, so the restoring force is mass proportional, as are your inertial forces. So it ends up that the mass falls away. We're able to achieve very light damping with that bare steel, which can be good in terms of acceleration responses, but as we saw, not so good in terms of displacements. Other sorts of devices, so actually here you can see people have looked at these coiled spring systems for this sort of equipment. When you move up in scale, so if you go to a floor sort of application, then you can start talking about lead rubber bearings potentially.
Scott, I have another question.
Go ahead.
Sorry, you mentioned vertical acceleration, or at least I saw it in your presentation, and you know, but base isolation, the structures are very stiff vertically, traditional structures. And so there may be a vertical component, depending on the earthquake characteristics. Have you had an opportunity to look at that yet, or is that something that you have maybe in mind down the future? Because I think in this isolation system, there's no vertical restraint to try to prevent maybe even uplift, right?
Sure.
Of the cabinets. It's something that maybe has to be considered in the long term.
Sure, definitely. So yeah, the vertical acceleration, so the ones that I was actually referring to were just induced by horizontal motion. So again, because we're using a pendulum mechanism, we get these vertical accelerations caused by the horizontal motion. So you can only imagine that if you had a large vertical component, then those are going to be directly transmitted. So potentially magnifying the induced vertical accelerations, or even, as you say, there's no restraint. So unlike, for example, a lead rubber bearing, where you are able to accommodate tensile loads potentially, here we cannot accommodate a tensile load. So it would come down to whether or not your dead loads are sufficient to sort of keep you in contact at all times. And this is definitely a topic that we're very much interested in. We've been looking at a little bit up till now.
Oh, okay, yeah, thanks, Scott.
Thanks, Jim.
There's another question in the chat. The study was developed unidirectional. Do you have plans to test with 2 accelerations in plan as well as vertical?
Yeah, so that's sort of following on with Jim's question. So traditionally, the models for these sorts of systems have been unidirectional models. So you know, sort of what we've seen coming from the test that I presented today is even if you're shaking in a single axis, you still develop multi-axial responses and rotations. And so actually we have a setup here at OU where we're going to start doing tests under biaxial motion. So that's going to be the sort of the first level of extension. And then because there is this interest in vertical motion as well, trying to incorporate that too. So incorporating 3 axes of disturbance.
Scott, out of curiosity, you know, in Oklahoma, they've had the earthquakes. We talked about this in the past because of you know, various, I guess, issues there. Are there any applications for regions other than what we traditionally think, like being in Western United States, in other areas that, that you have sensitive equipment so that there's a broader impact than what we normally would think about?
Yeah, I guess for those that are watching this that didn't know, Oklahoma's recently had a very rapid increase in seismic activity. On the whole, the events are quite small, so application to Oklahoma may be a little bit limited. We have had some larger events approaching magnitude 6. And in fact, we actually have data centers here as well. So Google has a data center here in Oklahoma, so they may be interested. Other applications other than sort of data centers that I keep referring to are different telecommunication facilities, potentially some transmission, so electrical transmissions. Another application that I'm interested in actually taking this work potentially is looking at wind loading. So should there be some sort of impactive load due to windborne debris, could these actually help in that case as well? So there are definitely other applications, but the primary focus of these systems really is west coast of the US, Alaska, and then other places across the world that are traditionally known for their seismicity.
Oh, okay. Yeah, thank you, Scott.
We have time for one more question. If anybody wants to unmute, ask verbally or write it down in the chat. We'll just give another minute or two. Okay, Jim, I could say we could wrap it up. So if you want to, any closing statements?
Well, I wanted to, this is Jim again, Jim Rickles. I wanted to, first thank Scott for the, I think, very interesting seminar of some prior work he's done and ongoing and future work. It looks like it's going to be very important to consider his work because of the need for resiliency and the stakeholders having this demand of creating a resilient community. So, again, I wanted to thank you, Scott, for that and the effort you took to prepare your slides. I think it was very informative, and hopefully this was of value to the participants that were able to listen in. And if you have any follow-up questions, perhaps Tommy, follow-up questions, I guess they could direct it to us and we could forward them to Scott if you wish, or
either way, they could go directly to Scott or to us, and we'll forward.
However you want to do that. We don't need to be in the middle of things. So with that in mind, I think I'll let everyone go, and keep in mind, our facility is an open access facility, and so we welcome people to visit our facility, potentially discuss projects they want to propose at NSF. We'll provide information for you and try to advance earthquake engineering, multi-hazard engineering. So if you need to contact us, you can visit our webpage, and we'll have some other seminars that will be coming in the future, and we'll give you advance notice by the advertising. So with that, I'll go ahead and let everyone get back to their other activities, and thank you again for attending, and thanks again, Scott.
Thank you, Jim.
Okay, that concludes today's seminar. Thank you.